Okay, good morning. This is Professor David J. De Los Reyes. Okay, I got a long video format. Discussion is, it will be an alternating current circuit long video format discussion. So for those of you who are taking up electrical engineering, this is for you guys. Okay, let's proceed. The subject matter will be alternating current circuit. This is now lesson number 12, and the title of the topic will be higher power factor. Okay? What's the significance of higher power factor and the utility bills we are paying to the electric companies? So I will show you how we will, minimize our payment for every bill that we will pay to the power companies if we do something like this. Okay, let's proceed. The given example, we are given the total lighting loads to be 10 kilowatts. So meaning we are given a house or a business entity and the total lighting load is 10 kilowatts. The power factor of that entity or house is 60% lagging. So meaning the inductive load of the house or entity are motor loads. So it could be air conditioners, okay, or some other motor loads equipment. The voltage of the source, we assume that this house or entity is in the United States of America, so the voltage of the source will be 120 volts. Okay? The problem is asking for I with the subscript old, meaning the old current, I with the subscript new, meaning the new current, S with the subscript old will be the old apparent power, S with the subscript new will be the new apparent power with the given condition. The condition of the problem is, if the new power factor is now 95% lagging. So the problem is asking for us to compare the total current consumption and the total apparent power drawn from the utility line if the original power factor, which is 60%, will increase to 95% lagging. So in here, we will show you that a higher power factor will be good for the people of the world. Okay, let's proceed with the solution. Let's try to bring out the power triangle originally. At the 60% lagging power factor, the power triangle will be this. The real power we draw from the utility line due to this lighting load is 10 kilowatts. It's a real power, right? And there is an inductive load, okay, in which the power factor is 60%. Okay? So if we try to add this 10 kilowatts plus the original reactive power of the motor loads at 60%, okay, this will be the total apparent power. And according to our computation, it is 6.67 kVA. Okay? Meaning to say, at the power factor of 60% and the true power of 10 kilowatts, the total current that will draw, or the total apparent power that will come out will be 16.67 kVA. That's a very big power. kVA is 1000 volt ampere. So it seems this is equivalent to 16,670 volt ampere. Okay? I will show you how we come out with this one. For the next power triangle, the lighting load, so we cannot do anything with the lighting load. So when the frequency changes or when the power factor changes, this kilowatt will remain still at 10 kilowatts because lighting loads is not controlled by frequency, right? So this P old will still be equal to the old true power, which is 10 kilowatts. So originally this is 10 kilowatts, and for the new power triangle it's still 10 kilowatts. For the reactive power, the problem is asking is that if the power factor will go up to 95%, so if it goes up to 95%, it seems maybe we have put something like a, what do you call this? A Q sub C over here to contradict this one, to increase that power factor 60% to 95%. Okay? Maybe the solution, we add a Q sub C to reduce that 60% or to increase that 60% to 95%. That's the reason why. Okay, so I will remove this one for the meantime. So for this to increase, actually, we add up a Q sub C to contradict the original reactive power of the motor loads. So it will increase to 95%. So for the new power triangle, this portion is actually lesser. It is smaller than this one. So if we try to get the total apparent power at the power factor of 95%, it will be the vector sum of this one plus this one. And what comes out as per our computation is 10.526 kVA, or this will be 10,526 volt ampere. Right? So you could see that if the power factor rises up, the total apparent power will decrease. Okay, this because originally it was 16.67 and this is now only 10,527, a difference of almost 5,000 plus. So that's lots of power. Okay, it's actually wastage in energy because if you do not increase your power factor from 60 to 95%, you will still be paying that wastage in energy. Okay, and to reduce the wastage in energy, we must have to increase the power factor to 95% by adding a condenser maybe in parallel with our utility line. Okay, let's proceed with the computation. The definition of power factor is actually the ratio of true power over apparent power, that is by definition, right? Actually, I gave you 4 formulas on how to compute for the power factor, but for this problem, I will be using the first one. That is, power factor is the ratio of true power over apparent power. So if we try to compute for the apparent power, algebraic manipulation, right? We put this S on the left, then we put power factor underneath. So S now will be true power over power factor. Okay, I will now try to compute for the all total apparent power at total apparent power when the power factor is 60%. So I will place it here, S with the subscript all. The kilowatt is actually 10 kilowatts, and the all power factor is 60%. So 10 over 0.60 will be 16.67 kVA. It is this. It is big, right? And if we try to compute for the current drawn at this load, we use the formula total apparent power is the product of the total utility line voltage times the total current drawn. Okay? So if we try to compute for I, it will be the ratio S over E. So I now with the subscript all will be the ratio S over E. First condition, all condition. The S odd is actually 16.67. We convert that to volt ampere. So we multiply that by 1000. Okay? For it to be volt ampere over 120 volts. Volt ampere over volts. So volt cancel. So what comes out will be ampere. So the ratio, the unit here is amperes. So 16.67 times 1000 over 120, that will be 138.92 amperes. Meaning originally, when the power factor is 60%, the total apparent power drawn from the line is 16.67 volt ampere, or 16,670 volt ampere, and the total current drawn is almost 140 volts, 40 amperes. Okay, let's go with the new condition. For the new power triangle, if the power factor now is 95%, okay, let's try to compute for the total apparent with the subscript new, right? The new total true power is still 10 kilowatts. So this is 10. Okay, 10 kilowatts. The new power factor which we would like for us to save economically, it will be 0.95. So 10 over 0.95 will be 10.526 kVA. Okay? So this 10.526 kVA is this one. Right? And this is less than 16,670. So at the new power factor, the total apparent power, okay, which will give us a bill from the utility companies is only 10,526 volt ampere. And if we try to compute for the current, we still use same formula, S equal to EI. So I now will be S over E. So that will be the total new apparent power is 10,526 volt ampere. Because if we try to multiply this by 1,000, no more K, right? So this is 10,526 times 1,000 over 120. And what comes out for the new current will be 87.72 amperes. This is now, this will now, compared to the original current, which is 139, it's almost half. Okay? So actually, by maintaining these motor loads, we could reduce the total apparent power by almost 5,000 volt ampere, and we reduce the current by almost half the original 138.92 current. So what they call this, the benefits that we will get for a higher power factor is that higher power factor is economical for the people of the world. Okay, that's it, guys. So for those of you who are taking up electrical engineering, this is for you guys. If you want to subscribe to my channel is at youtube.com/@ProfDavidJ. If you want to share it, please click share. Even those people who are watching YouTube, this is for you guys. It will benefit you economically on the power bills coming from the utility line. Okay, good morning from Los Angeles. This is Professor David J. De Los Reyes.